What if the solution to our energy crisis is not buried deep underground, but orbiting silently above our heads in the darkness of space? Imagine power stations the size of small cities unfolding in orbit, converting constant sunlight into clean energy and beaming it down to Earth around the clock. No clouds, no night, no fuel, just an endless river of sunlight redirected to where humanity needs it most. This is the promise of space-based solar power, a radical idea that could turn space into our next energy frontier. But can we really light our cities with power beamed from orbit? Or is this just another beautiful science fiction dream? On this episode of Beyond Delta 5, we explore how space-based solar power could become humanity's next giant leap for energy and why the race to build it has already begun. For more than a century, our civilization has been fueled by what we can dig out of the ground: coal, oil and gas, compressed over millions of years. These fossil fuels powered industry, transportation, and the digital revolution, but they came with a hidden bill: pollution, climate change, and finite supply. As global populations grow and developing nations demand more electricity, our need for power is rising faster than ever. Yet the fuels we rely on are finite, and the climate consequences of burning them are already reshaping coastlines, weather patterns, and ecosystems. So we turn to renewables, building vast solar farms and forests of wind turbines to capture clean energy from sun and air. But sunlight on Earth is intermittent, blocked by night, clouds, and seasons, and both solar and wind demand enormous areas of land and sea. Batteries and grid storage help smooth out this variability, but storing enough energy for entire regions is still expensive and technically challenging. Nuclear power offers dense, low-carbon energy, yet public concern, waste management, and high upfront costs keep it politically and economically complex. And on the horizon, there is fusion, the dream of harnessing the same process that powers the sun itself here on Earth. Despite exciting milestones, practical fusion power plants remain decades away, and humanity cannot afford to wait that long to decarbonize. So we face a crucial question. How do we deliver massive amounts of clean, reliable energy without consuming more land or waiting for technologies that may not arrive in time? One answer may lie above our atmosphere, where sunlight shines more intensely and almost continuously. In space, there are no clouds, no weather systems, and no night to interrupt the stream of solar energy. Above the atmosphere, sunlight is about 30% stronger, and satellites in certain orbits can see the sun more than 99% of the time. Space-based solar power, often shortened to SBSP, aims to tap into this relentless stream of energy using giant solar collectors in orbit. These satellites would convert sunlight into electricity, then into microwave or laser beams, and transmit that power wirelessly down to receiving stations on the ground. On the surface, huge antenna farms called rectennas would catch the beam and convert it back into grid-ready electricity for homes, industries, and data centers. In theory, a single large solar power satellite could deliver the same output as a major terrestrial power plant, but with no fuel, no emissions, and minimal land footprint. Instead of scattering solar farms across deserts and farmland, we could place most of the hardware in orbit and use lightweight arrays on the ground to receive power. Because the power from space is nearly constant, every hour of every day SBSP could serve as a clean baseload source, firming up a grid heavily supplied by intermittent renewables. The result would be a smoother, more resilient energy system that relies less on fossil fuels and less on massive storage infrastructure. But if this concept is so powerful, why have we not already built these orbital power stations? The first challenge is sheer scale. The solar arrays needed to deliver gigawatts of power would span kilometers, far larger than anything we currently launch in one piece. To build them, we would need to launch thousands of tons of lightweight structures, solar cells, and power electronics into orbit at a cost that must fall drastically below today's prices. This is where new heavy-lift vehicles like SpaceX Starship and Blue Origin's New Glenn could transform the equation, slashing the price per kilogram to orbit. Reusable rockets capable of launching massive payloads could make the idea of assembling city-sized power stations in orbit economically realistic for the first time. Once in space, these structures must unfold and assemble autonomously, using robotics and perhaps swarms of small construction spacecraft to snap modules into place. Next comes the core technical hurdle: efficiently and safely transmitting power across tens of thousands of kilometers without wires through our atmosphere. Most concepts use microwaves, which can pass through clouds and atmosphere with low loss, but require large transmitting and receiving antennas for safe low-intensity beams. Alternatives using lasers promise smaller hardware, but face challenges with atmospheric absorption, weather, and strict safety requirements for aircraft and satellites. Then there is cost. A single commercial-scale SBSP system could require investments in the tens or even hundreds of billions of dollars before delivering its first kilowatt-hour. Such a project would demand long-term political commitment, public support, and likely cooperation between governments, private companies, and international partners. Despite these hurdles, progress is no longer confined to theoretical papers and science fiction novels. Around the world, a quiet race is underway. In Japan, researchers have been studying space-based solar power for decades, conducting microwave transmission experiments and small-scale demonstrations. The Japan Aerospace Exploration Agency has published roadmaps that envision multi-megawatt demonstration systems in orbit, followed by commercial gigawatt-class power stations. China has announced ambitious plans as well, including test facilities for beaming power over long distances and a proposed experimental solar power station in low Earth orbit. Chinese state media has suggested timelines that could see prototype power satellites in the 2030s, positioning China as an early leader in orbital energy infrastructure. In the United States, NASA has revisited space solar concepts as launch costs drop, while the Department of Defense explores SBSP for powering remote bases and forward operations. In 2023, the California Institute of Technology launched a small demonstrator mission called MAPLE that successfully tested some key elements of wireless power transmission from orbit. At the same time, private companies in the US and Europe are designing modular SBSP architectures intended to take advantage of heavy lift rockets and mass-produced satellite components. For a channel like Beyond Delta 5, tracking Starship test flights and New Glenn's development is not just about rockets, it is about enabling entire industries in orbit, including space solar. If reusable heavy lift launchers achieve their promised cost and reliability, early pilot space power systems could arrive as soon as the late 2030s or 2040s. From there, scaling up to global impact would still take decades, but the first commercial beams of power from orbit could shine within the lifetime of today's young engineers. Yet, as with any disruptive technology, space-based solar power brings serious questions, concerns, and controversies that cannot be ignored. One of the most common fears is safety. After all, we are talking about sending powerful microwave or laser beams through the atmosphere toward the ground. Designers counter that these beams would be spread over large areas, with power densities comparable to midday sunlight, and safety shutoffs triggered by aircraft or objects entering the path. Nevertheless, convincing the public that these invisible beams are safe could be as difficult as engineering the hardware itself. There are also environmental concerns, including the impact of large rectenna arrays on land use, ecosystems, and migratory birds, though designs often allow agriculture or grazing beneath them. Strategically, nations may worry that space power satellites could double as weapons or be targeted during conflicts, raising the stakes for space security and international treaties. Who controls the orbital power grid? How is access priced? And could poorer regions be left behind if SBSP becomes the new oil of the 21st century? On the other hand, space-based solar power could be designed from the start as a shared global utility, with capacity dedicated to disaster zones, developing nations, and remote communities. Beyond geopolitics lies the ethical question of priority. Should we invest trillions in orbital energy, while many people still lack basic access to electricity on the ground? Supporters argue that developing cheap, abundant, clean energy from space could ultimately lower global electricity prices and accelerate development everywhere. If these technical, political, and ethical puzzles can be solved, what kind of world might space-based solar power actually create? Picture cities where energy is so plentiful and clean that electric transportation, desalination, and carbon removal become routine parts of daily life. Cheap, reliable power beamed from orbit could drive new industries, from green hydrogen production and vertical farming to advanced computing and off-world manufacturing. On the environmental side, replacing fossil fuels with SBSP and terrestrial renewables could drastically cut greenhouse gas emissions and slow the pace of climate change. Over decades, that shift could mean fewer extreme weather events, more stable coastlines, and a healthier biosphere for future generations. Geopolitically, nations that import most of their energy today could become more self-sufficient by hosting rectenna sites and buying access to orbital power rather than shipping fuel. Shared international SBSP projects could even become tools of cooperation, similar to the International Space Station, aligning once rival nations around a common infrastructure. Looking further ahead, the same technologies needed to beam power to Earth could also send energy to the Moon, Mars, or orbital shipyards, fueling the broader space economy beyond Delta V explores. In that sense, investing in SBSP is not just an Earth project, it is an infrastructure bet on humanity becoming a true spacefaring species. From our current vantage point, space-based solar power sits at a crossroads between daring vision and hard reality, between the physics that permit it and the economics that still resist it. We know the sun delivers more energy to Earth in an hour than humanity uses in a year. The question is whether we will build the systems to capture enough of it, even if that means reaching into space. As launch costs fall and orbital construction becomes routine, concepts once dismissed as impossible start to look like the logical next step. Space-based solar power will not solve every problem, but it could become one of the pillars of a diversified, resilient, and sustainable global energy system. The real decision lies with us. Do we accept the risks and costs of building power stations in orbit, or continue relying on the fuels that shaped the last century? Standing on the threshold of this new era, perhaps the most important question is not whether we can beam power from space, but what kind of civilization we want to become. If you want to follow how rockets like Starship and New Glenn could unlock space-based solar power and the broader industrial future of orbit, you are in the right place. Subscribe to Beyond Delta V, join our community of space enthusiasts, and stay tuned as we track the missions, technologies, and bold ideas pushing humanity beyond the next frontier.